Hello, I'm Sihang. This is an overview to our work, cross-failure bug detection in persistent memory programs. First, I'm going to talk about the benefits from persistent memory. Persistent memory features high performance, addressability, and data persistence. Persistent memory provides better performance, not only because it is faster than conventional storage devices, but also because it can allow programs to bypass OS interactions, such as file systems, by directly accessing the data in persistent memory. So programs need to ensure cross-consistency of persistent data. In other words, the program needs to recover to a consistent state in case of failure. So we conclude that direct access to the persistent memory benefits the performance, but makes it harder for programming. To support persistent memory programming, hardware platforms introduce new primitives. This figure shows a memory hierarchy where the cache is volatile and the memory is persistent. A persistent memory system first provides a durability guarantee, that is, the write can become durable in memory on demand. In this example, the write updates to cache line X. To make the update durable, the program first issues a cache line writeback or CLW instruction and then uses a store fence or S-fence to guarantee its completion. And the second guarantee is ordering. That is, one write becomes persistent in memory before another according to the program's requirements. In this example, a write updates to cache line X. To make sure X becomes persistent before the next update, the program needs to follow the same sequence of CLW and S-fence, and then write to Y. Also, write it back to memory after that. So in this way, the write to X is guaranteed to be persistent before write to Y. With the hardware support for persistent memory and many other programming support built on top of the hardware, it is still hard to program for persistent memory systems. The programmer not only needs to come up with a cross-consistency mechanism, such as a commonly used undo logging mechanism, but also needs to correctly implement it. Because of difficulties in persistent memory programming, we want to test whether the program is cross-consistent or not. Our previous work, PM test, tests these two fundamental properties in persistent memory programming, that are the durability guarantee and the ordering guarantee. In the example of undo log, the programmer can assert whether the log has been persisted in the end of the sequence, and if the log is persisted before updating to the log's value bit. But only ensuring the correctness during the normal execution is not enough. What if there's a failure? The program needs to correctly recover from the failure and then resume the execution. To address these problems, in this work, we introduce the idea of interactions across the failure. We divide the program execution into two stages. The first stage is the pre-failure stage, where the program is performing normal execution. If there's a failure, the failure goes to the post-failure stage, the stage after failure, and performing the recovery and the resumption of the execution. We refer to the interactions across failure as cross-failure interactions. If there's any incorrect interactions across failure, the program may not recover to a consistent state. So the program may have cross-consistency bugs. Therefore, a holistic testing across the failure is necessary because both stages across failure are equally important. To detect incorrect interactions across failure, we provide XFDetector. Here is the workflow. First, the annotated program is injected with failures by XFDetector. And for each failure point, XFDetector traces PM operations during both the pre- and post-failure stages. And then, XFDetector detects if there's any incorrect interactions across failure by checking if the post-failure stage is reading from inconsistent data left by the pre-failure stage. To evaluate detection capability, we validate XFDetector with synthetic bugs first. We inject these following bugs in the micro-benchmarks, and then, during testing, we find new bugs. With simple test cases, such as inserting an item to a key-value store, we found 3 bugs in PMDK examples and 1 bug in Redis. And with our recent work, PMFuzz, a test case generator, we found more bugs. We found 11 additional bugs in PMDK examples and 1 more in memcached. In summary, a persistent memory program consists of 2 execution stages, a pre-failure stage and post-failure stage. The 2 stages are equally critical to the cross-consistency guarantee, because if one stage is incorrect, the program may not recover to a consistent state. We provide XFDetector that detects incorrect interactions across the pre- and post-failure stages. We recently released a new version of XFDetector at the following link. The new version has better backtracing support and has an improved debugging capability. Thank you.